All right, welcome back, everyone. So for today's main seminar, we have Alessandro Carotenuto from the Università di Parma, who will be more or less who will be talking about quantum tangent spaces and tangent reduced decompositions. Take it away.
Thank you for the introduction, Ben. And of course, it's always great to be back in Prague. And also want to thank Antonio as well, because he took care of I would say, the hard part of the work, which is to introduce most of the theory of well groups and reduced decompositions. So, okay, some of you have already seen most of this talk, probably in Brno. And so apologies to the ones of you that have already seen, but I mean, I also took this as a good excuse to add some more details, so to give you a better flavor of what are the kind of braid group manipulations, and that one has to do in order to achieve these results, which is the classification of quantum tangent spaces for a Drinfeld-Jimbo quantum group through the use of these so-called tangent reduced decompositions. So, okay. So yeah, first of all, this is a work in progress, and it's a collaboration with Paolo Papi and Christopher Holweg. And in a way, it is the continuation of the work that we started here in Prague about the non-commutative differential geometry of Drinfeld-Jimbo quantum groups. As Thomas was saying last Tuesday, we really like differential calculi, and all in all, this work is again about classifying differential calculi for quantum Flagg manifolds. And the interesting part, I would argue, is that in a very natural way, as we shall see in a moment, a question in non-commutative differential geometry was first translated in a question about the structure of quantum groups, and then once translated, we were able to give it as to present it as a problem in combinatorial algebra. And I would argue that this somehow showcases some genuinely quantum behavior. So these structures that we are going to see in a moment, and namely, especially the convex order on the sets of roots and all the game that we do with the braid groups is not something that you can see classically, at least not in this context. So, first of all, let me remind you some things that already Antonio mentioned. So we will make use at the same time of different order relations that come to play when we deal with sets of positive roots of a semi-simple Lie algebra. In particular, so first of all, we have the notion of the Brouat order or weak order of the Weil group. So suppose that we have an element V in the Weil group, and we have reduced decomposition. We say that V is smaller than W with respect to the Brouat order if there exists a reduced decomposition of W, which starts with the reduced decomposition of V. Otherwise, we also say that V is a prefix of W in this case. And this is an order relation that I have on my Weil group. Then we have a second order relation, which we have on the set of roots. So suppose that beta and gamma are two positive roots. Delta plus for me is the set of positive roots. We say that the gamma is less than beta in the partial order. Sometimes I will refer to it as the usual partial order of delta plus. If beta minus gamma is in the positive span of the set of simple roots. Here, pi for me is what was phi for Antonio, is the set of simple roots of a Lie algebra G. And somehow more central here is the notion of a convex order on a set of roots, which depends on the choice of a reduced decomposition in general of an element of the Weil group. So suppose that we have an element of the Weil group. As Antonio was saying before, we have an order on the set of inversions, which is this guy. So I take as first root the root corresponding to the first simple reflection. Then the second is the first one acting on the second, and so on and so on. And this is what we call the set of inversions. And I will denote by this sign less with the I on the bottom to mean that this is the convex order induced by the reduced decomposition I on the set of roots. So, and the order is just given by the order in which the roots appear when I follow this recipe, this way of producing them, this algorithm. Sorry? Yes, yeah, I mean, in a way you can, so if I ask your question, basically two different convex orders are as close as the corresponding two reduced decompositions are. So Matsumoto theorem, in fact, is a way to compare the different orders. We shall see in a moment how this has consequences on the set of positive roots, of quantum root vectors. So in particular, okay, so like what can happen here? I can have, okay, let me comment on this because it's important actually. So the simple case is that I have a first reduced decomposition, and I have a braid here, and I have a second reduced decomposition. By the way, I will confuse a lot between just using the indices or using the reflection and so on. So suppose that I have a reduced decomposition I prime, which is the same as I, except that I substitute this braid here with the inverse braid. And this braid could really be anything. It could even be just a commutation, or it could be a short braid or a long braid. Well, what happens is that if I take the set of inversion of V, so these are both reduced decomposition of V. What happens here is that I have the same order set, except that if I call alpha the root associated to the first element of the braid, and I call beta the root associated to the last element of the braid, what happens here is that when I pass from I to E, they get exchanged. Okay, so that's how I compare different orders using the braid relations.
Maybe after the question, is there any logic in calling a braid like a bracket? Or is it just a way to...
I mean, it's a notation. It's notation, and it's very useful notation, I would argue, when you are doing this. Yes, exactly. So usually you also put an M here to remind yourself how long is this braid.
But it's very far from the type of lever, right?
No, don't think of it as a lib bracket. No, it's yeah, somehow could be misleading, but yeah. So I don't know if that answered completely your question, but okay, let me. So why do I insist of calling this convex order, in fact? Because there is some convexivity property here. So in particular, suppose that I have beta and gamma that are two positive roots in the set of inversion of a given element of the Weil group. And also suppose that beta plus gamma is itself a positive root, then it follows from the definition that we have given before. One has to work it out a bit, but it follows that beta plus gamma is in fact an element of the inversion set, and that we have that beta plus gamma is contained between beta and gamma. Okay, what does it mean if now we take as the element of the Weil group the longest element, W naught? Well, this means that first of all, we have a total order on the full set of positive roots of the Lie algebra, because the set of inversion of W naught is the set of positive roots. And also this means that if I have beta and gamma, the convexity relation tells me that either I have that first come beta, then beta plus gamma, and then gamma, or vice versa. And in fact, one can alternatively study reduced decomposition by looking at this convexity property on the set of positive roots. And what Paolo Papi proved in the 90s is that we have a one-to-one correspondence between the convex orderings that we can put on delta plus and the reduced decomposition of the longest element of the Weil group of G. And so this was something that was somehow very relevant for beyond the Drinfeld-Jimbo theory, was something that people found very important to study, for example, quantum loop groups, where one has to give a theory of reduced decomposition when the Weil group is in fact infinite dimensional. Yeah, to my knowledge, it was less used in the study of non-commutative geometry of the Drinfeld-Jimbo quantum groups. So here I want to I will be super brief in presenting what is the story that is on the back. What is the story, the non-commutative geometry requirements that that we had at the beginning of this research when Raymond asked me to check the differential calculus for quantum GDU. So, as Antonio was saying, we have this notion of a quantized enveloping algebra, which is presented in terms of relations and generators. I was even more lazy than Antonio. In fact, I didn't include any of the relations, not just the set relations, but you know what they are, and if you don't know, it's fine. And we also know that this is an Hopf algebra, and here I gave the value of the coproducts on generators just to set notations. So in particular, you can see that K is a group-like element, and also what is important is that for me, the coproduct of EI has a Ki on the right, and the coproduct of Fi has a Ki minus 1 on the left. Okay, so the drill is that now we can define the quantum coordinate algebra of G, which happens to be the unique, simply connected, complex Lie group associated to the Lie algebra G. And we are interested in studying the first-order differential calculi on OQ of G, which means that we are looking for an A bimodule together with a derivation that is generated in degree 0. What happens is that in this case, one can describe dually, in a dual manner, the notion of a first-order differential calculi by looking at these objects that are called quantum tangent space. So for us today, a quantum tangent space is a subspace of the quantized enveloping algebra, which is basically a left coideal, meaning that the coproducts of the elements of T length inside of T plus C tensor OQ of G. So today we are interested in left differential calculus, which means that we are interested in left quantum tangent spaces. And of course, you have a right version of everything. Oh. Yes, and B equals C. Yes, here in the tension, in third point, B equals C famously. Exactly. I guess. All right. So The idea of Riemann a few years ago was, why don't look for quantum tangent spaces in some theory that is very established, very well representation theoretic, as the theory of Lustig quantum root vectors that you have seen from Antonio's talk before. And here I am giving a bit of I'm summarizing a bit what are Lustig quantum root vectors. So we have a representation of the braid group of G on the quantized enveloping algebra. It is a representation through algebra homomorphism. And somehow, as Antonio was commenting before, this representation basically gives you sets of nested commutators that get more and more convoluted the more complex your Dinkin diagram is. So here, Antonio first showed what happens in the simply least case. Now I show you also what happens when the Dinkin diagram has this form, or what happens when we are dealing with G2. Okay, so the important point here is that this representation of the braid group does not give a coalgebra homomorphism. We have to invent something in order to study how to study the coproduct of Lustig quantum root vectors. So yeah, these are the quantum root vectors of Antonio have already mentioned. And also, let me tell you something important. For any reduced decomposition, the quantum root vector gives me monomials that give a PBW basis of the quantized enveloping algebra. So as you can see already in the quantum world, we don't have one PBW basis. We have different PBW bases according to the choice of reduced decompositions. So as I was saying, now before that, as we were commenting before, the set of quantum root vectors depends on the choice of reduced decomposition. I have different reduced decomposition, and they differ by braid relations. So first thing one should ask, what happens when I use a braid relation to pass from one reduced decomposition to the other? What happens to the set of quantum root vectors, right? So first of all, the simplest case is when I and I prime only differ for a commutation. Okay, in this case, as you could probably expect, we have an equality of the two sets of quantum root vectors. I prefer to work with the Fs, with the negative quantum root vectors, but of course, the same happens when we consider the positive root vectors, the E. Okay, now what happens if I do something more interesting, if I actually use a braid relation? So for example, if I pass from S1, S2, S1 to S2, S1, S2, well, what happens is that it's basically the same that happens at the level of roots, right? So everything that is not contained, everything that is a quantum root vector not attached to one of the root outside of the braid is not touched. Then what changes is the root that are the roots that are considered, the quantum root vectors that are contained in the middle of the braid. And they change in this way. So this is the way we have a change of PBW basis correspondingly when we pass from one reduced decomposition to the other. Yeah, so here you have a reduced decomposition which has a braid here. You will have a quantum root vector attached to this root, to the root in this position here. And I also index quantum root vector with the reduced decomposition. Then you have, let's say that we have a simple braid, okay? So I am in this situation, A and B. Then in the middle, I have the root, the quantum root vector attached to this root. And then I have this one. So what I'm claiming here is that by extreme position, I mean these ones. So this quantum root vector, when I take the braid, they just get exchanged. Okay. So I end up in, where is the, yeah. So now what I get here is that this goes in the first position and this goes in the last position. But as vectors, they are the same vectors. Whereas here, we got a generally new quantum vector. Exactly. Yeah. And this will be quite relevant later. So this is exactly what happens in the, as you can, yeah. So this is to say that every change that you have from one reduced decomposition to another is local in a way, because it really depends on whether the quantum root vectors that you're considering are attached to the braid that you are changing. So the other guys are unchanged, untouched, exactly. No, this was figured out by Tingley, I found it explicitly written for the first time in one of the papers of Tingley. Yeah, and of course it's the same also when you consider a longer braid, a braid of type B2. Yes, and if you're in type B, a braid move could change 2 vectors, but that's it. Yes. So the math. Exactly, yes. In G2, you have these 3 vectors in the middle and they will get changed. Exactly. Exactly. And that's it. Yes. And yeah, if from one reduced decomposition to the other, I always pass using braid moves, and that's how I get some control of the change of basis, right? Okay. So the idea of Raymond was that one can look for reduced decomposition such that the corresponding quantum root vector, okay, here multiplied by k beta, but it's just some normalization in a way, such that I was saying the corresponding quantum root vector span a quantum tangent space. And in fact, we have some non-example first. So this does not happen for the reduced decomposition, even in the simple case of A3. So here we can see that if I take the coproduct of the fourth root vector, the root vector attached to the fourth root in this reduced decomposition, in the middle I have some product of 2 root vectors, meaning that the quantum tangent space condition is violated. I don't have a left co-ideal anymore. But also, luckily, we have some positive results, because Raymond and Peter Somberg showed that for case AN, there exists 2 reduced decomposition that give rise to 2 quantum tangent space on UQ of G, spanned by the respective negative quantum root vectors. And these reduced decomposition are somehow the most natural you can think about. So first you take 1, 2, n, then 1, n minus 1, and so on. So this is the ascending reduced decomposition, and then correspondingly you have the descending reduced decomposition. So in this project, we are interested to generalize this to classify the reduced decomposition that give rise to quantum tangent spaces and to describe them combinatorially. So how much time is left with you?
No, maybe 30.
30 minutes, okay. Okay, so in order to understand how to generate quantum tangent spaces, one has to understand the coproduct of general quantum root vectors. And it's always good to start from rank 2 cases, right? So this example of a quantum root vector that is not a simple generator is just a Q commutator, Fj, Fi. And if one computes its coproduct, we can expand by using the fact that the coproduct is an algebra homomorphism. We have different terms that appear here. And what happens is that, of course, I got this wrong. Yes. So this should be Fi, and this should be Fj. But what happens is that for the quantum root vector Ti Fj, so the one that will correspond to the element of the Weyl group Si Fj, here what survives is the quantum root vector Fi, and on the left tensor product with one with Fj on the right, and I don't have the other contribution. And actually, one can observe the same kind of behavior for other quantum root vector associated to root system of rank 2. If a quantum root vector can be written as Ti on Fj, then I always will have something with Fi on the left of the tensor product and something with Fj on the right. So somehow this is telling us that the coproduct is seeing the order, the convex order associated to the set of roots. And in fact, this is basically everything that you need to know in order to study the coproduct of general quantum root vectors. Yes. Well, because this is the root vector Ti Fj, meaning that you were starting here from some reduced decomposition of W naught that starts with Si, Fj, and so on and so on. And what happens here is that you have on the left side of the tensor product the root vector attached to this root alpha, which is smaller in the convex order, first of all, alpha plus beta, and then by convexity to beta, which is the root. So this is the root attached to this second guy, and this appears somewhere after. So, in fact, this is the same that happens also when you look at B2, when you look at C2, right? We are familiar with this. Well,
let's say that basically you take the product of the vector corresponding to beta, you're going to get also alpha plus beta.
yeah, exactly. I'm coming there. I'm reaching there. Yes. But this is to say that the one first observes this in rank 2, and in order to prove it in full generality, we have to reduce a general quantum root vector to some rank 2 commutators. And in fact, this can be done. Maybe I will skip. I will go fast on this slide to go to something more interesting. This can be done by studying the relative Weyl group generated by the last two elements appearing in a reduced decomposition of our elements of the Weyl group. So what happens, in fact, is that it turns out that the coproduct of quantum root vectors respects the convex ordering. So in particular, if I take the coproduct of a negative quantum root vector, this can be written as a sum of such terms, where here on the left, I only have products of quantum root vectors attached to roots that are smaller than beta k in the convex order induced by I. And on the right side, I have only quantum root vectors attached to roots that are bigger than beta k in the convex order induced by I. So the summation is all the possible ways to do it, possibly with zero. In fact, the second step is to understand what are the coefficients that are actually zero and what are the coefficients that are not zero. So the coproduct is separating what comes first from what comes after. And if I did the same process for the positive root vector, so for the E's, I would have somehow the reverse situation. So on the left side, I would have the guys that are bigger. On the right side, I would have the guys that are smaller. That's how it is. So yeah, in order to have a quantum tangent space, I'm only caring about the left side. I would like that only one guy appears on the left side of this expansion of the coproduct. Okay, and in order to understand when this happens, we have to study a bit deeper the Weyl group and and some aspects related to Brouat order. And so what are we doing? We want to be able to read the coproduct of a quantum root vector just by looking at its expression in terms of the braid group acting on simple generator. Problem is that a quantum root vector can be written, in fact, in many different ways using the action of the braid group. So the idea is that roughly we want to write the quantum root vector in the shortest way as possible. And how one does it? This is basically using braid relation. Let's see this example. So I'm starting from this braid root, from this quantum root vector, T1, 2, 3, 1 on F2. And what I do here, first I am doing what? First, I know that I can exchange T3 and T1 because this is a representation. Then I can use a braid because this is a representation. Then I'm here. Then I have this sort of braid where instead of having the action of a generator of the braid group, I have an F2 here. And what happens when you have this sort of half of a braid is that this is equal to F3, plus minus, doesn't matter. And then you can use the fact that T1 is trivial and you have effectively written this quantum root vector in a shortest form. Now we can check the coproduct. And what happens when we check the coproduct is that I know that in the coproduct, F2 will land on the left and F3 will land on the right. So yeah, exactly what I said. So how do we formalize this? We start from our element in the Weyl group, and we can look at this set. So what is this set? This is the set. Okay, so I'm starting from some truncation of the longest element of the Weyl group that corresponds to my quantum root vector. And we can look at the set of elements that are smaller than my truncation, WK, such that the root beta is contained in the set of inversion of V. And it turns out that this set has a minimum. And if I take a reduced decomposition of this minimum and I write the corresponding quantum root vector, I get the same quantum root vector I was starting from. So this is the shortest way of writing a quantum root vector using Brouat order. We are going to call over line WK the projection of WK along beta. And if SJ1, SJL is a reduced decomposition for the projection of WK along beta, we call this a reduced expression for the quantum root vector. And moreover, we're going to call the elements Fj eta such that eta is smaller than beta k in the new convex order, in the convex order induced by the reduced decomposition of the minimum element, prefix root vectors of f beta k. We also require here that theta is smaller than beta k in the partial order on the set of positive roots. Okay. So with the notation introduced above, we can now make a more precise statement about the coproduct of f beta k. It turns out that in the coproduct of fi beta k, which is equal to fj beta k, by the way, you can decompose the coproduct in this way. So here you have the prefix root vectors of fi beta k, and here you have something else. So here you have, and also what is important is that the CI are non-zero Laurent polynomial in Q. Okay, so let's stop for a moment. What is our strategy now? We want to have a coproduct where I only have single quantum root vector corresponding to the reduced decomposition I, and I don't want any kind of product of elements here. Thank you. The F tilde is just some polynomial expression which has weight beta k minus beta I. So it's not a quantum root vector, it's some polynomial in UQ and minus, UQ and minus, yes. It could be just one quantum root vector, but often it's just some monstrous polynomial here. But we don't care about what happens on the right. We only want to give a good structure to the left side. Back to mathematics. So then in order to have a quantum tangent space here, we have a quantum tangent space if these guys are actually equal to the quantum tangent space, the quantum root vectors of my starting reduced decomposition, and if these guys disappear. So let's see some two non-examples. Let's see what can go wrong, actually. So first, we take this reduced decomposition Q12, 312. And if I take the coproduct of Fi theta, theta for me is the highest root. So in this case, it's alpha 1 plus alpha 2 plus alpha 3. I get this quantum root vector Fj of alpha 1 plus alpha 2. Now, when I use the, what was his name? Sorry again. When I change basis from the what? Tingley, thank you. When I use the results of Tingley to pass from the PBW basis corresponding to J to the one corresponding to my starting I get that here I have the product of two guys appearing here. So I don't have a quantum tangent space in the end. Okay, so here what happens is that things don't work because I am somehow using a wrong basis.
I think here on the top is even an if and only if.
Yes, it's an if and only if, actually, yes. Second example, everything works now from the point of view of having the same quantum root vectors for your starting reduced decomposition and the reduced decomposition corresponding to the minimum. But you have that these here are not equal to 0. In fact, you take this reduced decomposition 132, 132. Again, you take the coproduct of the quantum root vector corresponding to theta. And what happens is that here you have the product of F1 and F3. And there is nothing you can do here, right? Because this decomposition is actually already, if you truncate to 132, this is already the minimum element in the Weil group corresponding. So this is already the projection along theta. But here inevitably you have the product of two quantum root vectors. So again, the tangent space condition fields. Yes, yes, because what happens then? What happens then is that one of these two guys, excellent observation actually. What happens is that if you take this braid move, one of these two guys will jump over your highest root. So you can't possibly have this term. And in fact, it gets cancelled when you pass to the new reduced decomposition. You have a new Fi theta, generally different from the one that you have here. And in the coproduct order, that Fi theta, you don't have this term. This term does not appear, can't possibly appear. Okay, so what does it mean this on the combinatorial level? Can we translate these two requirements in requirements on the reduced decomposition of W naught? Well, yes, because in the form we are going to call I a tangent reduced decomposition if, first of all, for the projection of any truncation on W naught along beta k, WK is as an initial section of the convex order of the starting reduced decomposition. This is a way of translating combinatorially our requirement that the prefix root vector of Fi beta k are actually the quantum root vectors corresponding to the reduced decomposition of W naught. Second requirement is that if we have that beta k can be written as gamma plus delta, where gamma is a smaller root than beta k in the order induced by the decomposition of its projection, then we have to check what happens to the simple roots that appear in the expression of delta. Right? Every delta can be written in a unique way as a sum of simple roots. And we want that each one of these simple roots has to be greater than beta k with respect to j. The theorem here is that the quantum root vectors span a quantum tangent space if and only if I is a tangent convex order. Of course, we didn't give this name randomly. Okay. Well, what can we do about it? First of all, we can already prove something without even putting the pen on paper, that if we have that G is of type G2 F4 NDA, there exists no tangent. Sorry, this was the old version, I guess. There exists no tangent reduced decomposition. So for G2, maybe with a lot of calculations, you can prove it by hand. For F4 and D8, if you try to check all the reduced decomposition, they are some thousands reduced decomposition, maybe millions. So it's not something that you can do by hand, but with our classification, these just follow from the fact that condition 2 requires that a reduced decomposition, a tangent reduced decomposition should start from a cominuscule root, which means that it's a root that has coefficient 1 in the expression of the highest root. And there exists no such root for the case G2 F4 E8. So two-line proof. Not bad. So another important result is that actually we can give explicitly these tangent reduced decompositions. Because remember that we have the two reduced decomposition gives the same set of quantum root vector if and only if they are in the same commutation class. So we are going to give a representative of the commutation class of each tangent reduced decomposition. And how is it done? Well, this is a construction that can be described in terms of thinking diagram in a nice way, I would say. So for a simple root alpha, we can consider the while group generated by the system, the root system, where after I remove alpha I, which pictorially can be told as I don't know, let's do Dn, why not? I am taking a node of my Dinkin diagram, and I am considering the Dinkin diagram that comes from removing this node. Okay, so far nothing difficult. So we have this particular element, which I called D of pi. Why pi? This should be S. Sorry, pi is equal to S now. So D of Si, which is the longest element of my starting while group time the longest element of the white group of this Dinkin diagram where I have removed one node. And so, of course, we can iterate this construction. I can now remove another node. I take D of pi minus I, and this should be I and J. And it turns out that this gives me a way to construct this reduced. So first of all, it's a well-known result that these elements have a unique up to commutation class reduced decomposition. And I can use this fact to construct a reduced decomposition of W naught. So first of all, I take a cominuscule node inside of the Dinkin diagram of my Lie algebra, and I take the corresponding element. Then I look at the new Dinkin diagram. I take a cominuscule node in that other Dinkin diagram, and I take out another cominuscule node in the Dinkin diagram, and I have another element, and so on until I exhaust my Dinkin diagram. And this gives me, so it turns out that this gives me a tangent reduced decomposition of my quantum, a tangent reduced decomposition of W naught. And we call this canonical tangent reduced decompositions. And the theorem that I didn't write is that every tangent reduced decomposition is commutation class equivalent to a canonical tangent reduced decomposition. Okay. So let's see an example. So first we start with A4, and I decide to take, I can do it, yeah. So if I do it with A4, and let's say I first take out the root 2 here, I have to take out the root 2 or the root 1 in there. Yes, I can write W naught as D 2 pi. And then I go on, I take out the root 1. So I have D of pi minus 2, 1. And then I take out the 3, yeah. And then the last one. No, this is minus 2, this is minus 2 and 3. No, 1. Sorry. And this is how I get a reduced decomposition. But we can do better, actually. Why don't do it with D6? So here I've written the highest root, and we can see that I only have one cominuscule root. No, I have two cominuscule roots, in fact, sorry. And I can take out either the node corresponding to alpha 1 or the node corresponding to alpha 5. Let's say I take out the one corresponding to alpha 1, and then I get a D5 Dinkin diagram. And now I can go further. So now here I have three cominuscule roots, and I can take out either. And again, I end up with an A4 Dinkin diagram, and so on and so on. And this gives me a way of writing a tangent reduced decomposition. So this is a reduced decomposition that gives me a quantum tangent space for E6. And I will say that this is all for the moment. So now we know how the non-commutative geometry is connected to the combinatorial algebra of the Weil group, at least at the first order. Of course, the dream for the future will be to expand this. As Raymond has repeated many times here, we know that there exists a maximum prolongation of a first order differential calculus. So in the future, a project will be to describe combinatorially also the dimension of a maximum prolongation. We recently found that there are some connection with bosonization. Giovanni is working on them and doing an impressive job about it, I will say. But these are stories for the future. And for the while, thank you for your attention.
Right. Questions for Ale?
So you said before that for E8 and some other the algebras, there is no possibility of starting with a reduced decomposition of the longest element of the Weil group and indeed obtain a tangent space. I mean, of course, this does not mean that you cannot have a tangent space.
No,
you can have it, but you cannot have a tangent space that behaves, let's say, like the tangent space to the underlying Lie group, if you want, in terms of the dimension at least.
So you mean on the flag manifold?
No. I'm really
on
about
the
Lie
Lie
group
group
itself.
Yeah, this definitely means that.
Geometrically,
at least if you look inside of velocity quantum root vectors, this means that you should add, for example, degree 2 generate products of two generators in order to have a quantum tangent space, meaning that you have a dimension that is more than classical.
Yeah, I see. Okay. Yeah.
Zero dimension always works, yeah.
Okay.
Yes, because here I can't really start this process because let's do it for G2. For G2, I only have two nodes, and I would like to take out one that is cominuscule. But for G2, the highest root is this one. So as you can see, there is no simple root that has coefficient 1. So I can take either of these nodes out to start my process. If I understand your question.
I mean, I think the only thing I can manage is just turn it off and then turn it on, and then I know it's on. So I understand, right? You're taking the co-minuscule node, you are thinking diagram, co-minuscule, choose whatever one you want, cross that, then repeat the process for the various components, and then that will keep on giving you that will give you a reduced decomposition.
Yes.
And by choosing the co-minuscule, that gives you this reduced decomposition.
This element of the Weil group, which has a unique reduced decomposition.
But it's the quotient of the Weil group by.
It's the longest coset representative.
Yeah, in the associated.
In the associated,
quotient.
yes, in the quotient, yes.
So
you can think of it like that, yes.
Question then, going back to what I was saying to Bishan, if we know from the A series case that there were guys which give you tangent spaces, but whose dimension is not classical.
Yes.
So that means that the reduced decompositions that give you tangent spaces, such as the maximal prolongation is classical dimension, or a proper subset of the tangent space decompositions you guys have. Could you make a naive guess just from the Dinkin diagrams which ones would be special? I mean, because if I remember
my guess is that somehow this has to do with the order in which you do this process. So you start from a cominuscule node, and then you probably have to take out some cominuscule node that was connected to the one you started from, and so on and so on. So this should give you a prescription about the order in which you do this.
And then if we look at the A series, if I do that across the first guy, then the second, or I move the first, then the second, and the third, or I go the other way, we get the two reduced decompositions that Petter and
Exactly. So if you do this cominuscule game for the A series, and you first take out the first node, and then you take the second, blah blah, until n, and you get exactly your reduced decomposition that you know to work.
So you should follow this path somehow. If you jump all over the place, then it should mess up the classical dimension.
Yeah, exactly. Like somehow you should always create a connected Dinkin diagram at each step.
Aha, yeah, of course. Yeah. Okay. And then what? Think about it. If I do D4, what happens? I come all the way along, and then I come to A3. And then I have two choices. I put this one or this guy.
Exactly.
And if I start at the edge, then I take this, then I should take this, and then I go along. Yeah.
Something like that, yes. So you should consider all the possible paths in which this can be done.
So that would mean that for A and there are two.
Yes, this will be.
For D, you probably have three.
Probably. I can't see it right now, but probably there are three.
Yeah. It would just be three. Okay, thank you. It's a nice picture.
As usual, my question is, what about affine Lie algebras or cut smooth?
So yeah, I was thinking about that. So to the best of we can probably expect so what is the fundamental result here? I will say is that this rule of the coproduct, right? That it separates everything based on the convex order. And I will say that this is probably still true at the level of affine Lie algebras, even though you have now an infinite Lie group. And so to understand if we can then study the coproduct using this rule here, we have first to establish if it's true that you have the projections along the roots, also in the case of the affine Lie algebras, which is probably true, because even though the Lie group is infinite, here you are working at finite steps using the truncations. So it should still be possible to prove that the projection along the positive roots exist. But we haven't really thought about it.
Yeah, so my question would be, so here you are only looking at quantum tangent spaces that lead to left covariant calculi, right? So could it be possible that some of your tangent spaces are not giving you a left covariant calculus, but a right covariant one? Or like, can you also see which of the left covariant ones are even bicovariant calculi?
So yeah, thank you. So first of all, when do I get the right covariant calculus? I have to be able to study the right side of the coproduct as well as I do with the left side. And in principle, one will say, what is the difference here? Well, the difference comes from the fact that I'm using the left action of the braid group. So it's easy to start to study the minima, the projection along the descents by using the minima with respect to the Brought order. Whereas it's not clear to me, so here the elements that appear here should come from some maximum, in fact, with respect to the Brought order. But it's not easy, it's definitely not stated in the analogous way as the projection. Why? Well, what is the element such that I start from Vk and I want an element greater than Vk in the Brought order, such that beta is contained in its set of inversions. Well, this element exists. I know that it exists because it's the longest element of the Weil group. So you have a trivial answer every time that you try to do this. So somehow you have to play some tricks in order to study the right side of the contents of the tensor of the coproduct.
Usually you would think that like left covariant and right covariant should be just a simple symmetry kind of.
Yeah.
So
Yeah, but here, as I said before, the symmetry is broken by the fact that you are not dealing with a right action. We are dealing with a left action of the braid group.
So you would have to spell out everything using the right action, and then probably you would get something similar.
Or maybe you can play with the inverse reduced decomposition, which will be, so you have the reduced decomposition I and you have a convex order. Of course, if I reverse a convex order, I get again a convex order. And you can ask what is the reduced decomposition that corresponding to this one. And this is the inverse reduced decomposition. And probably you have to study that one and the projection along the roots of that object in order to understand the right side of the coproduct.
I was just asking because somehow here you are throwing out some of these possible quantum tangent spaces because they are not left, so they don't lead to left covariant calculi, but maybe they lead to something else that is interesting, like to a right covariant calculus. So maybe could be worth also thinking about that.
Also, like every time that you have a left calculus, you have a right calculus, and vice versa. So by the antipode. So
by the antipode.
Somehow
right.
I was not worried from a non-commutative geometry point of view. I was more, okay, so this question of the right side of the tensor product is interesting from a combinatorial point of view, but
is this true? Like, but that.
Yeah. Exactly, yes.
In that sense.
Yeah, but of course there could be applications in which you are interested in both sides of the tensor product at once. So it's definitely something worth investigating.
Okay. So I see this with left and right, but then yeah, you're not looking at all at bicovariant calculi. This is not.
I am not looking at all at bicovariant calculi. So first of all, my conjecture is that you have bicovariant, or at least at the logistic level, only in the A series, and this will be correspond to the two reduced decomposition found by Raymond. Not that these are coalgebras. So is it not enough that the tangent spaces are coalgebras? Sure. Okay. So yeah, should be studied in some different way. I see. Yeah. I mean that. Yeah, right. That one has classical dimension, so it can be right. Sorry, my bad.
You're just looking at the positive and the negative here. There's no cartan. So somehow to be bicovariant, you have to have some
I never
cartan.
thought about it. This is actually an interesting question. How do I understand reduced decomposition that give me a bicovariant calculus?
I've been thinking about it and never really getting anywhere. It is interesting.
It is interesting.
Yeah,
Okay.
But you need a third ingredient. Like you don't, I mean, Lustig gives you the negative and the positive root vectors, but doesn't say anything about the cartan. And that's the hard part. I mean, for SL2, for quantum SU2, we know one is E and one is FK.
Of course,
We've
of
known
course.
that for 40 years. But yeah, it's the cartan in the middle we don't know.
Of course.
No, they're not, because I mean, if you take the case of SU2, you get E and you get FK. They're the two, the E's and the F's. So you've got a two-dimensional guy, and it's not bicovariant, because you need to add in a third piece in order
But
to make
one
it
can try
bicovariant.
to understand even just at the holomorphic or anti-holomorphic level.
If you just look at that, then I think this is the picture.
This is the picture, but I
Yeah.
don't know how. Like, this is definitely
I mean, this
should
is
be some combinatorial rule again, but it's not entirely clear to me.
I have no idea how to add on the cartan.
Yeah.
Yeah.
Any questions from the online audience?
So I have a question. So maybe a different generalization. So you described quantum tangent spaces for UQG, and then we have quantum tangent spaces for the quantum flags, and you can either obtain them as subspaces as a dual of the flag, or you can consider the quotient UQG induced by some Levy subalgebra. And the Levy subalgebra is a pop subalgebra. And now I wondered what happens if you look at more general right co-ideal subalgebras. So this would go towards quantum symmetric pairs. Do you have any idea of a way how to construct quantum tangent spaces on the induced quotients of those? So maybe the easiest example would be the non-standard Podlesh.
Okay, so if I understand your question, okay, I guess I understand at least the direction your question goes, like, can I classify the reduced decomposition that give me a quantum tangent space on a quantum flag, maybe not upstairs, but when I project down, I get a quantum tangent space. And I think that this could probably be explained in terms of factorization of the reduced decomposition of the Weig group with respect to the parabolic subgroup that defines the quantum flag. About the quantum symmetric spaces, I don't know. I don't think the technology of quantum tangent spaces just falls down when you look at quantum symmetric spaces in general. So one has to invent something else.
So one idea I had, or not really idea, but so these quantum symmetric pairs, they sort of relate to Satake diagrams, and maybe can do something with those, but I have no idea.
Maybe. I mean, one should definitely include Satake diagrams in whatever will be the description of differential calculi for symmetric pairs, but I guess we're very far from any kind of answer.
Yes, thank you.
Like the non-standard Podlesh, we don't know, but Thomas Brzezinski and myself are getting somewhere. We need to put a bit more time into it, but there is a first order calculus that looks correct, and we think, I mean, there's a no-go theorem from Podlesh that says you won't get anything that looks like a Hodge diamond. So you're going to have to sacrifice something when you go from first order to second order, but a picture is starting to emerge. But it'll be a more general structure than a calculus. Hence, you'd have to consider more general things than tangent spaces, like Ali said. But yeah, even for the simplest example of a kind of non-standard flag quantum symmetric space, quantum non-standard Podlesh, it's very much work in progress.
So what is the more general structure if you don't consider differential calculus?
Work in progress.
Okay, I see. Thank you.
Right. I guess we will just end it there and thank Alessandro again. And we will be back next week with Tatiana Schulman as our seminar speaker. See you then.